Or 3.
Just to make sure that we're all. First one said. Share the fun. All right. It says, in the cases, if any is negative. Keep going.
A, B, D, F, H.
A and H. Yes.
Because the indicated point is below the x-axis.
Is the velocity 0? If any is the velocity. Yes? Yes. We know that. The acceleration 0.
Hey.
Hey.
Because the slope is constant. Constant. It says that we can't have an acceleration over 0.
Blame it on you. Yeah.
The indicated point of E also has acceleration.
That's a
No, it's not in the plan.
Okay, hold on. Let's work through what's going to happen on E. So on E, if we have a velocity versus time graph to match E, what is that going to look like?
At point E.
Well, just the whole thing's looking there. So here's a slope.
Increasing velocity.
Positive and
Decreasing.
decrease. Does that make sense? Positive, decrease, positive, 0, and then it's negative. What is that graph going to look like for the velocity versus time graph? No, just draw your finger.
Is this a straight line?
Let's look at what we had before. So this is what we did last time, remember? Right? It's like this thing. It's like this thing, part, right? And then it's like this thing to the second part. Does that make sense? Because remember, we could show this. Really, going to be what? Down. Does that make sense? Yeah, it's going to be a straight line down. So if I go back here, okay, so that's going to go something like that, and that's the indicated point that they're talking about, right? And what is the acceleration versus time graph going to look like?
This is straight negative line.
Right, because the slope here is
Negative.
negative and
Decreasing. Well, it's negative and constant.
negative. The value of the slope is negative and constant. Negative. So now going back to the question at hand. Acceleration 0. zero
At that.
anywhere here.
No.
No. Is that okay? Yeah. The only time that you're going to have zero acceleration is when the slope of the position versus time graph is what? So it's is that okay? Yeah. All right, F. This was the one that I found to be the hardest. For one of these cases, if A is the acceleration negative at the indicated R1, who wants to do it? Yeah, what you got? Okay, so which one's D and F? D and F. And tell me the reason that I would agree with that on F. Does that make sense? So the slope is negative and it's getting more and more negative. What do you guys think about that? Okay? Yeah, this one is negative, negative, negative. So I think absolutely. And again, you could use your velocity. Yeah, this one, the velocity is negative, but it's getting closer to what? Zero. Does that make sense? So I'm gonna go with not D. Does that make sense? I think this one has a positive at that. But I think that F is true. Michael, go ahead. I think that's like C, F, and H. So you agree with F? So let's talk about C next. Let's look at C. So he says C. What do you guys think about C? Does C have a negative acceleration, Peter? You said yeah. Why did you say yeah?
Because the velocity is increasing at a decreasing rate.
Yeah. Does that make sense? So absolutely. So this is like positive velocity, but it's going down, right? So it's going in the positive direction, but it's going in the direction that pushes negative acceleration. Absolutely. And then which one did you say? H. What do you guys think about her H? Do you agree on H? It's the same thing, right? Yeah. So we're okay on that one. Because acceleration is negative. What do you guys think about E? Yeah. So it should be. And we didn't get that. Like, this was the one I was like, boy. I just had but so we didn't get that rules on it. But now we know.
But it's getting more popular, so it's approaching to
Does that make sense? So these guys All right. Cool. Okay, you can pull your notes out. We're gonna do some free fall stuff today. I got some problems. No problem. Okay. So first of all, now, that's why I like it, but I didn't
Easy to the textbook.
What's that?
Easy to the textbook.
Something. It takes time.
Yeah.
Edited by Carmeling, right? Yeah. There we go. There we go. Yeah, maybe. Maybe not. We'll see. Okay, so free fall. Here we go. Here's the beauty of free fall puzzles. We are experts. Right? You can imagine three, I use them. All exactly the same, right? It's just instead of having the next direction, we're talking now about things going in the y direction. So, in their problem, acceleration. Acceleration. So we're talking about gravity, assuming that the problem is placed on Earth, sea level, gravity is going to have a what? And the what direction? Negative. Right, but we're going to make it downwards, negative. Now, if you want to be that only child, that's going to be positive, that's fine. But then you have to take into account and not, I'm going to call it downward as that's what
But if we do that,
as opposed to okay. This no. Okay. See the problem. I don't know. An accelerated test about a guy on the moon who has a feather and a right? And he lets them know what happens. Whoa! And then why do you have a feather on Earth right here and right in front of you?
assuming it's not ours.
Well, they might go right now. No, they're not right. No. No, it does not. So, okay. Assuming no air resistance, and we do that unless there's other, okay? You will not see any mathematical questions, any computational questions that will ask you to take it unless you take physics C with me, okay? But really, okay? All objects will fall at the same rate. Really, what is it about the hammer that makes them fall at different So I want to look at a few conceptual questions. I'm going to give you a couple of moments to look at these by yourself, and then we'll discuss them with our partners. So take a look first by yourself.
The velocity.
Are you ready? Shall we discuss? Okay. Issue number one first. Which of these motions is not what's the expression for this? You're correct. You're correct that it's a consequence. Yeah, absolutely. I'm just giving my team to tell you what I'm getting. Let's do number 19 first. Number 19. Can I have a zero velocity and non-zero acceleration? I want to retrain you. You can do. Let's talk about yeah. Right. Yeah. Does that make sense? What if you use the graph to analyze that? Yeah. Awesome. Absolutely. So I feel like exactly what? So how do you know that the whole time? I said here is we do up, so velocity stop. I said here is number 20. Get an object of zero non-zero velocity.
This happened in my English class the other day too.
The people are pulling.
Yeah.
That's rough.
You talked to me before. Occasionally.
When the velocity is constant. So like, I don't know, like a car going down the street like 40 miles an hour.
No.
This one is always contentious. So I want to know where we're at in this. Vote. So here. I will tell you, my friends, this is the kind of I'm trying to see. This is the kind of thing you want to do. Okay? All right, Keegan. Are you here to defend your honor?
Yeah.
Go.
Wouldn't it be equal because he's taking resistance into account? Declaration is always in the direction of the motion.
Okay.
When it's being thrown up, the air resistance is acting in the opposite direction of down. So when it's that, air resistance is pushing down well, it's thrown up. When it's coming down, the air resistance is pushing up. And since it's the same object, the surface area doesn't change. The air resistance is going to be both. It's going to be equal in both cases. And since when an object is thrown vertically upward and it comes back down without air resistance, it's the same. The air resistance is equivalent going up and down. Wouldn't the speed stay the same?
Okay. Do you guys understand what he's saying?
Yeah.
Says there's some symmetry there, just like there was symmetry if there's no air resistance, right? Okay. Go.
Okay, so I'd say it would have a less velocity when it goes because if when you throw it up at a certain acceleration,
Keep talking, yeah.
if you throw it up, the air resistance is pushing down because, and so that would reduce the like reduce the velocity of like the
Okay. Sure.
down, it would also have that reducing the velocity of the object. Now, so at the same point, put it up at an acceleration of 5 meters per second, it can come down at the same velocity that you threw it up at. because there's acceleration, there's the force of friction, or in this case, resistance on the object. So it's and velocity.
All right, we've heard two good arguments, one for each side. Have they swayed you? No. Ben's like, I got one. Will? He's like,
No.
Anybody else want to make an argument?
Can we draw some stuff?
Yeah.
Sure, let's draw some stuff.
Draw some things.
Some stuff and things?
Yeah. All right.
Draw some free body diagrams?
That would be
That's a
cool.
good idea.
When you don't know what to do, always draw a free body diagram, right? Yes. Let's draw some free body diagrams. So here is our object on the way up. What forces are acting on it while it's going up? What's one?
Force of the earth on the object, which is
Yeah. Should call it a ball. Okay. Are there any other forces acting on it as it's going up? Yeah.
There's the applied force, which is.
No, we're letting it.
Oh, sorry.
No, right up.
let it go.
Force of friction. No.
Let's go.
Air resistance.
Against motions off. This might be something you want to write down. Not that you're gonna like memorize, but it's the thought process that I really want to aware of. Air on the ball. So the net force acting on the ball is equal to the force of the air plus the force of gravity. They're both acting in the same direction. Do you agree?
Mm-hmm.
And they're causing some sort of acceleration in the downward direction. Is that okay? I'm going to call this the acceleration on the way up. Just so that I can distinguish it from. This is a magic ball. So when you're going down, right? Whoa!
Douglas.
Amazing. On the way down. Gravity. Yeah, which way is that one going? Down. Okay. What else you got? Probably because the question's all about it. Where is this going in this? Up. Because it's resisting the motion. Isn't it nice when you draw pictures? Pictures make everything better. Pictures should draw them more often, like every time. So that's the force of the air plus the force of gravity is equal to the mass times the acceleration. If they're in the same direction, you agree?
Yes.
What about here? No. Which way is the ball accelerating?
downwards.
Down. FG minus FA.
Yes.
You add it, right? If it's in the same direction. So I'm going to write this is FG minus FA is equal to M times the A on the way down. And I'm going to write this as FA plus FG is equal to M times A on the way up. So just based on this, what can you tell me about the accelerations?
Different.
They're different. Okay, now let's write down what we know. Which one's bigger?
The first one.
Acceleration for up is bigger than acceleration for down. Is everybody okay with that?
Yes,
But that doesn't answer our question, does it? No. You said what would. Let's get there. Now, I'm trying to think about the easiest way to think about it. If this is my ball and I throw it up and then it comes back down, what is for the same? Going up and coming back down. The what? The distance. I'm going to write that down because that's interesting. Displacement, distance for now. Distance going up and the distance going down are the same. Okay? velocity, right? So let's talk about velocity. We know the initial velocity coming going up the up. And what's the final velocity for the up part?
Oh, not zero.
No, yeah. So the up part is zero. The initial velocity for the down part is zero. And the final velocity for the down part is really what we wanted to know, right?
Yes.
We wanted to know, this is what we're arguing about, is this the same as this? Or is it bigger or is it smaller? So we're just going to find a relationship. We're going to ask you, do you have an equation that has acceleration, initial velocity, and final velocity? I bet you do. Somebody says,
As v is
wow. What was that?
as v squared
Okay.
equals vi squared
Okay.
plus 2a times x minus x.
Where did you get that from?
So we probably have it written this way. Vx squared equals vi squared plus 2a delta. That's probably
Oh, wait, I
do you
got
see
it.
that? Okay. So let's make it
Yeah, that one.
equal. So let's say Vx squared minus Vi squared over 2a in the up direction has to equal Vf squared minus Vi squared over 2a in the downward direction. Is that okay with everybody what I just said there?
Yeah.
Yeah, because these are both the distances. We can do it. First question, does anything go away? Anything else go away? You have twos in both of them, don't you? Let's get rid of the twos. And now we just want to know a relationship between VF and the VF on the right hand side and the VI on the left hand side. So I'm just gonna, I don't know, maybe write it like this. VF squared over VI squared is equal to A down over A up. Is that okay what I just did there? That was a lot of stuff that I just kind of algebraized there. Is that a verb? To algebraize? In case you're shaking your head no. You don't even like, I had emotions telling you something. What? Casey Masters Dictionary, I don't care. All right. What do you know about A down and A up? Okay, A down is less than A up. So what do you know about this thing right here?
Less than 1.
This thing is less than 1. So what do you know about this thing here? It's less than 1. And if it's less than 1, what do you know about VL?
They're not equal.
They're not equal. So do you understand what we're talking about? This ratio is less than 1. So that means this ratio has to be less than 1. What's up?
Oh, see, algebra size.
Well, this is bad.
It's
That's a bad Sure? Okay. So what's the right answer to the question that we just were trying to answer? There you go.
I definitely got that from free body diagram.
Well,
And
good.
I understand.
But okay. So here's the thing. As long as you understand how to get it, question. That's a good AP Physics 1 type question. Just saying. All right. I want you to do this problem real quick. With your partners, go. Then you have a different acceleration. Right. Then the ground is pushing. Do you? You know time. You know the initial velocity. You know. So here is the lovely. What do we get? So 51.8. We okay? Okay.
Well, everything.